you will be able to find the recording available from Save on Energy on the training and support website. Right, I'm going to admit a few more people and then we will get started. So thank you everyone for joining. This is the Save on Energy webinar on key energy savings measures for existing building commissioning projects. My name is Jess Burgess from Canadian Institute of Energy Training. We've also got Monica Tang from the IESO, as well as Eddie Cloutier, Aurélie Verstadt, and Megan Wallace from BPA here as your presenters this afternoon. This will be, we've got a 90-minute agenda, quite a bit of content around those energy savings measures and how to identify them. Before we get into that, we'll just have a really quick update on Save on Energy programs from the IESO and take a quick look at a couple of the new websites with information about the EBCX program, as well as training and support resources about existing building commissioning. Then we'll turn it over to the BPA team to give us a quick run through regarding EBCX projects and the process for those projects overall. And briefly, what are some of the most common measures to look for, and then dive into how to identify those measure opportunities into the investigation phase of an EBCX project, where I think we'll spend most of our time together this afternoon. Then we'll have some time at the end for a short Q&A. If you have questions as we're going, I encourage you to use the chat. Please drop your questions in the chat. If they're good and timely, and we've got, I'm sure all of your questions will be good, but if it looks like we will have time for them, we will jump in and take them as we go. Otherwise, they'll be recorded there and we'll come back to them when we get to the Q&A. Great, then I'll turn it to Monica for some quick updates about Save on Energy programs.
Can we go to the next slide, please?
Yes. Are you seeing the EBCX resources slide?
No, we're still on the agenda slide.
Really? Is everybody seeing the agenda slide or slide 4?
I think it's
slide
probably
4.
A glitch. We see it, the slide 4.
You see slide 4. Monica, do you want to just, I think you might have steered your own. And so if you, yeah, perfect.
Sorry.
So I'll just be on slide 3.
3, yes. Okay.
Yes.
I think I can navigate. Anyways, okay. Well, welcome. I'm Monica Tang from the IESO. I am a business advisor for sector capability. I just wanted to let everyone know that there's going to be some big program changes to the retrofit program coming. So there, as of October 30th, most non-lighting measures have increased significantly the incentives. So some of them have doubled and some of them have gone up to 4-fold. And the last day to apply for lighting projects, both under prescriptive and the custom track, is December the 17th. The reason why is because we're launching the instant discounts program for lighting starting December the 18th. And in this program, we're going to be going to the distributors directly. So you, all the incentives will go to the distributors, and so there's no more going to be applying for applications and doing all that kind of paperwork. And if you want more information, you can go to the retrofit program website.
Great, we're on slide 4.
Perfect. Okay, and so the next item I wanted to touch on was the capability building program that we have. So this webinar is one of the resources for it. We also have other additional resources such as practical guides, info sheets, and incentives for up to 20 training courses. And the intent of the capability building program is to increase awareness and develop skills in organizations and communities across Ontario, and for people to participate in Save on Energy programs.
Thanks, slide 5.
Okay, so this EBCX program under Save on Energy has 3 different phases. And the first one, you would hire a commissioning provider, and you would get an incentive up to 6 cents a square foot, up to $50,000, or 75% of the costs paid. The second phase is the implementation phase. And in there, you would get 3 cents a kilowatt hour up to $50,000 and cap 30% of the facility annual electricity consumption. And the third phase is the persistence phase, and that is also 3 cents a kilowatt hour up to 30 cents a kilowatt hour. And it's capped at $50,000 as well. And Jess, if you can go on to the website to kind of demonstrate where our program is.
Yes.
So if you're interested in applying to the program, it's on our Save on Energy website, and there's at the very bottom of our EBCX page, there's a bunch of commissioning providers, some of which are on the call today. So you can reach out to one of them, download the list, and kind of get started, or you can email ebcx@ieso.ca if you have any more questions. And then we also have another page, the EBCX resources page, and this is where you can find this webinar as well as previous webinars that we've hosted. If you want to go down, there's also fact sheets and a practical guide for building owners and managers. Jody had a question. Will templates like the program reporting template? Sorry, let me just say.
Yep.
Be uploaded here. It's actually on the EBCX program page already. So at the very bottom of the page, it's there already.
Great. So that resource is on the first page we saw, the EBCX program site?
Correct. Correct. I can drop in the link.
Perfect. Great.
That's it. Thank you so much.
Thanks, Monica. And now we're going to turn it over to the BPA team, O'Haley, Eddie, and Megan, to guide us through a quick overview of the EBCX project process, and then dive into identifying some of those key measures in the investigation phase.
Yeah, so as we sort of touched on, there's the three phases, investigation phase, implementation phase, and persistence phase. If we jump to the next slide, the majority of our presentation is going to focus on the investigation phase, which is the phase where the EBCX agent will come in to analyze the system operations. They'll do diagnostic tests, and then they'll come up with a plan and propose measures that can be implemented in the implementation phase. Part of these measures will be to put together a findings log. This slide shows a flow chart of the investigation activities. So the EBCX agent will come in and do diagnostic monitoring. If there's a control system in the building, a BAS, a building automation system, the EBCX agent will look at reviewing and implementing trend logs, and as an option, if it's possible, to set up a remote access to the BAS system so that they can go and review how the building is operating sort of live. If required, they can add portable data loggers as well, if there's no building control system or if they need additional information. Other measures that might be taken, the EBCX agent would do with contractors. Example of this would be air balancing. They would bring in an air balancing contractor to take air readings so that you get a better idea of how the building is working. They will also review any available documentation, so plans and drawings, specifications, operating manuals, sometimes shop drawings if they're available from the initial installation. They will then move on to do functional tests, and the functional tests will be done seasonally. You'll do a winter functional test and a summer functional test, as well as functional tests through all 3 seasons, so winter, summer, and shoulder seasons. They'll also look, so we would do those on the main pieces of equipment, chillers, boilers, air source heat pumps, things like that, as well as functional tests on terminal systems. So your VAV boxes, fan coil units, lights, thermostats, things like that. And then we'll also do an audit of the, here it's called the light out audit. So what lights are staying on after normal operating hours and why are they staying on? All of these reviews and investigations will be compiled and put together into the next slide, into an investigation report. And as we mentioned earlier, that investigation report will include the findings log of all this investigation phase that we've gone through. It'll be presented to the owner. If the owner has any comments or wants any changes, we can reintroduce those back, update the report, and then we'll move on to the implementation phase. So we're just going to go through a few statistics of what we found doing EBCX. So the next two slides are based on a US Department of Energy study that looked at more than 100 EBCX jobs for different building types, ages, and sizes. The majority of the buildings were office buildings, but they did look at different building types. And you can see from this pie chart that almost half of the EBCX measures that were implemented were for air handling units. And another 25% were for the heating and cooling plants. So the boiler plant, chiller plant, cooling tower, and the associated pumps. The next slide shows what they identified as key measures for EBCX. And what they discovered was that there were 9 measures that contributed to 75% of the total savings. And so these 9 measures are listed here, and the majority of them are related to controls. So they looked at revising the control sequence, reducing the equipment runtime, optimizing the airside economizer, adding or optimizing a supply air temperature reset, adding variable frequency drives to pumps to allow for variable flow, reducing coil leakage, reducing or resetting duct static pressure set points, adding and optimizing start-stop times, and adding and optimizing condenser water supply temperature reset. And we're going to get into a bit more details of some of the more common measures in the rest of the presentation.
Thank you, Megan. So now what to look for during investigation? We can divide opportunities into 5 categories. We have equipment scheduling, outside air management, controls, maintenance, and heat recovery. We will discuss each category and present case scenarios to illustrate those issues/opportunities, how to spot them, and what measure we could implement in that case. I will start with the equipment scheduling. This is the first opportunity to address and the easiest saving measures to stop systems when they are not required. So how to spot that kind of issue? You can review building automation system schedules and compare it to actual occupancy schedules, review BAS graphics and trend logs, perform on-site inspection, if possible, also an inspection during after hours to spot other issues. You can conduct an interview with operations staff and analyze energy data. First scenario we present here, we are in an office building occupied from 8 a.m. to 5 p.m., Monday to Friday. And during the investigation, you see that air handling unit schedule is set from 3 a.m. to 8 p.m., 7 days a week. After discussion with the operator, the schedule was originally set to 6 a.m. to 5 p.m. Monday to Friday. but schedule was modified maybe 2 years ago during winter when tenants complained about thermal comfort on a Monday morning, for example, minus 20 degrees C outdoor, and it was just leave it like that. So in that case, what could be the measure to implement here? Of course, modify the schedule to reflect actual need. You can implement a special sequence, which is called optimum start. So here you want to start the system as late as possible. So the system will automatically start several hours prior occupancy during the coldest days of winter, but very close to occupancy time during mid-season. So here, that sequence will consider outdoor air temperature and indoor conditions. Finally, you want to train staff. So you want to train operation staff on BAS scheduling capacities to answer future needs. For example, for a special event during weekend, you want also to train staff to know about optimum start parameters. Here another case scenario to illustrate the unoccupied mode. You are in another building, and here you, during investigation, you see that HVAC schedules meet occupancy hours. When interviewing the operator, he does not receive any thermal complaints, even on the coldest days. So here everyone is happy, but analyzing energy data, you see that utility data shows a high base load during unoccupied hours, which is a sign that HVAC or other equipments are running at night and no one maybe knows about it. In that case, during the investigation, you can review trend logs and see here at left that maybe for the first air handling unit, the fan status does not follow command. So it is always on and you see during your inspection that the manual there is a manual override on the electric panel. So here is the answer. Then maybe for the second air handling unit in that building, you see that it is on automatic mode. So here it is authorized to run during unoccupied hours for night setback, for example, to maintain 18 degrees indoor, which is totally okay. But then you'll see reviewing trend logs that the outdoor air damper opens at night when the building is empty, which means that you need to heat and cool outdoor air when it is not required. Here, the system should be on recirculation mode. For that case, the measure would be to program a dedicated control sequences for HVAC operation during unoccupied hours. So yes, we can authorize air handling unit and perimeter heating to start during unoccupied hours, just to have to maintain minimum and maximum room temperature indoor. But you will have here a special attention to outdoor air damper and exhaust fan control. The air handling unit should be on recirculation and exhaust fan should be stopped at night. You can also program a preheating or warm-up mode, for example, to authorize outdoor air admission, maybe only 30 minutes prior occupancy. And finally, you want to train staff on that capacities to avoid future manual override. Here we have an example to illustrate the opportunity for equipment lockout. During your investigation, you analyze energy data and you see that energy consumption is very high, even during mid-season. The operator said that he received many thermal complaints, hot and cold, and also the BAS graphics review see that you have simultaneous heating and cooling. In that example, we have a heating coil that is on during summer with a supply air temperature at 39 degrees C. So there is a problem here. It was a very hot summer day and your heating is on, so maybe something is wrong, but still you want to avoid that situation and maybe establish an equipment lockout on heating coils during summer. For equipment lockouts, so we can have establish a boiler lockout during summer. You can authorize a boiler to start under a certain outdoor air temperature. You can also have lockout on terminal heating, perimeter heating during summer, and cooling coil valve during winter. Then you can review control sequences to reduce simultaneous heating and cooling during mid-season. Then the last example for scheduling opportunities is for lighting. Here we got a building and a night walkthrough reveals that the interior lighting is on despite lighting controls. Then the investigation revealed that the majority of occupancy sensors are faulty. So everyone saw that the light were off during the night, but it was not. The existing building measure, commissioning measure here would be to verify existing lighting controls and sensor, optimize lighting control schedule. Maybe you want to engage security staff, janitor, and cleaning staff, because for lighting controls, you will see that sometimes lighting schedules are extended to match cleaning hours, which is not optimal. And finally, maybe you want to set up an occupant awareness program for the lighting control. It would be like encourage tenants to turn off lights when they leave their office. So to summarize, for the equipment scheduling opportunities, first you want to optimize HVAC schedule to match occupancy and load during occupied hours and during unoccupied hours. Maybe you want to interlock fresh air and exhaust relief fans to unauthorize them to run after hours. You want to optimize lighting schedule to match occupancy, maybe review equipment selection and implement seasonal lockouts as we discussed.
Okay, the next measure we're going to look at is outside air management. So how do we? Well, we're going to review the HVAC schedules and review the BAS trend logs. So outdoor air dampers and VAV box operations. Review CO2 level monitoring if it's available. And we'll look at that for return air also at the zone level. Perform an on-site inspection and do functional testing. Do an interview with operations staff and review any problems that they may have, such as an antifreeze alarm. It's a common one. Compare the minimum outdoor air requirements to the actual outdoor air that's being supplied. And review the initial testing and balancing reports. And or perform measurements with a new balancing team to see what's actually happening in the building. So the first scenario we're going to look at is economizer control. So the schematic shows a typical air handling unit that has outdoor air being brought in and a mixed air damper or return air damper to control how much outdoor air goes into the system and how much exhaust goes out. And to optimize the economizer, we would increase the amount of outdoor air that we're bringing in when the outdoor air temperatures are optimal. So this is usually in shoulder seasons when we have cooler days and we need cooling on the inside of the building, and we can optimize bringing in more outdoor air to provide free cooling. Next slide. So some of the EBCX measures we do related to economizer control. We will restore or optimize the airside economizer. So we'll make sure that the economizer is sequenced with the mechanical equipment. You'll have to consider the dehumidification load as well. We'll look at the differential enthalpy with a fixed dry bulb control with a high limit shutoff. So an example of the high limit shutoff would be when the outdoor air is more humid than the return air and the outdoor air temperature is greater than 21 degrees. One thing to note is that in buildings where we have a heat recovery chiller, we want to prioritize the mechanical cooling when there's a heating demand, because that'll be the most efficient choice. Here's a scenario of building pressurization problems. And usually, these are happening when your doors won't open or close properly. So in cases where we're over pressurizing the building, where we have too much outdoor air intake, you'll notice that the outward swinging doors will stand open and will be difficult to close. They won't close behind people as they're leaving. The issue with this is that during the winter, the indoor air will infiltrate through the building envelope and it can cause moisture problems in the envelope. The opposite can also happen where there's too much exhaust and indoor facing doors or inward swinging doors won't latch properly. And again, you can have issues with your envelope with humid air from the outside infiltrating through in the summer into the envelope. So what we want to do is make sure that we have the correct amount of outdoor air for the building. So we can calculate the outdoor air requirements using ASHRAE 62, which is the guideline specified by the Ontario Building Code. And ASHRAE 62 has the building will have two separate outdoor air requirements. So there'll be the constant flow, the ones that have to go into the building, that's your base minimum. And that'll be makeup for direct exhaust. So for washroom exhaust, for example, exhaust that you need or outdoor air you need for building pressurization. Ventilation needs not based on occupancy. So minimum outdoor air per square foot of the building. Then there'll be a portion of the outdoor air required that is going to be based on your occupancy rate. So ASHRAE 62 says you need so many CFM or cubic feet per minute of outdoor air per person. And that can vary. That's a variable amount based on how many occupants you have in the building. We'll also calculate the outdoor air fraction entering the building when the air handling unit is not in economizer mode. So to calculate the outdoor air fraction, you take the return air temperature minus the mixed air temperature. So in this example, return air temperature is 21, mixed air temperature is 13, divided by the return air temperature minus the outdoor air temperature. And we get an outdoor air fraction of greater than 50%. So to summarize some of these measures that we were looking at was reviewing the minimum outdoor air flow requirements, so the design requirements versus the actual occupancy rate, review the outdoor air damper operation, and review the direct exhaust control functions. The next measure we can look at is demand control ventilation. Which would reduce the ventilation airflow rates as the occupancy levels decrease. And we use CO2 monitors to determine what the occupancy rate is. ASHRAE 62 says that it's the outdoor CO2 plus 700 parts per million to maximum of 1100 parts per million. Next slide. So some of the control strategies we can look at for demand control ventilation is that we can put a CO2 sensor in the return air duct. That doesn't consider diversity in the system though. So you may have a meeting room, full of people, and we wouldn't know that that room has a higher outdoor air requirement because you're only measuring the mixed air in the return air duct. So you can put CO2 sensors in these critical zones to identify if they have a greater need for outdoor air. The minimum airflow rate is still required, and you want to make sure that you have enough air for things like diffuser distribution to make sure that the airflow patterns are correct, and reheat. The VAV boxes will have a minimum position as well. And in this case, always remember to give priority to the economizer. So in the right conditions, you'll have lots of outdoor air. So to review the key measures for outdoor air management, you want to look at optimizing the economizer control strategy. Review the outside air emission versus the requirements. So the minimum outside air requirements, the airflow balancing and pressurization, and the outside air damper control. And also look at implementing a demand control ventilation system.
Okay, thank you, Megan. Next, we'll talk about control measure. As Megan said earlier in the presentation, control measures are among the most common in existing building commissioning. And there are almost as many type of measure as there are systems and way of programming them. Several methods will make it possible to determine which measure are applicable. First, simply viewing the control graphs will often allow you to notice anomalies such as manual control points or problem with temperature, humidity, or pressures. Programming and also analyzing trend logs will make it possible to detect measures such as system cycling. Trend logs will also allow you to analyze operating data outside of occupancy hours. Next, also, it's possible to do, and it's highly recommended to do functional tests on the different HVAC system and electrical system. It's another detection method. Very simple example of a functional test could be to physically validate whether a motorized damper opens at 100% when this command is requested at the BAS, and close completely when it has a 0% signal. Also, very elaborate functional tests can verify complete mode of operation of the system and see if they are as effective as they should be. Finally, interviews with operators and analysis of occupant complaints will also help pinpoint various control problems. Next slide, please. So a first example is on the speed control of pumps. In that case, you could have the same example with fans a lot of time. So in that case, the trend logs demonstrated that these pumps were always operating at relatively high speed. And the designer, unfortunately, had not specified any pressure set point during the design. So the contractor did the best they could, and they adjusted the operation with a relatively high pressure set point. This forced relatively high speed operation at all time, and even the need to operate in that case, as you can see on the graphs, 2 pumps in parallel, while they should not operate in parallel at all. The implemented measure made it possible to, well, basically we modified the programming of the pumps to analyze the demand of the different heating coils in the system. So the pressure has been dynamically adjusted so that when heating demand is low, the static pressure set point is automatically reduced. This measure makes it possible to significantly reduce the speed of the pumps and, of course, their energy consumption. Next slide. Similar measure on ventilation system. Here you have on the right the schematic representation of a typical variable flow ventilation system with terminal reheat. So basically each VAV box will reduce its flow to a minimum, and if necessary, of course, the terminal reheat will start working to make sure that the supply temperature is not does not produce overcooling in the rooms. So in that case, what we had was that the operator was always operating the system at a fixed supply temperature set point at 55 degrees Fahrenheit or 13 degrees Celsius. And what it caused in that case was that there was a lot of partial occupancy of this building. So a lot of reheat was needed at all time, even during the summer. So next slide, please. What you could do in that case is to implement a trim and response strategy. So basically, you are looking at the different VAV boxes, and you are looking if a lot of them are over 90% open. And if it's the case, you will reduce the supply temperature. And if it's not the case, if there's a very low cooling demand, you will gradually readjust the supply temperature by increments of 0.2 degrees Celsius or 0.5 degrees Fahrenheit, for example. And it will make it possible to do energy saving by reducing the need for terminal reheat. Next. A very simple scenario in that case, based on the trend curves recorded at night, there was no temperature setback in a specific building. And the operator said that the wall insulation was so bad that doing temperature reset was creating a lot of complaints from occupants. So that was the reason why the temperature setback had been deactivated. So what was done in that case, of course, it's a real concern having bad insulation in the walls, and it's true that it can create occupancy discomfort because you will have very cold wall and it will create thermal discomfort. So the temperature was still set back to 18 degrees Celsius as soon as the occupancy schedule ends. However, the system was programmed so that when the outside temperature was under -10, the room temperature was set back to normal earlier in the morning to make sure that when the occupants arrived at their desk, the temperature was close to normal. And of course, it's always appropriate to train the operator to adjust the way the system is doing the setback instead of just deactivating it. Another type of measure that is related to controls, and this is one that we see really often in all type of building. Every VAV boxes has basically two set points. There's a maximum set point, maximum flow set point, and a minimal flow set point. And it happens quite often that the minimal flow set point was not specified during the design. And in that case, we had a building where all VAV boxes minimum set point were fixed at 50% of the maximum, which is relatively and usually too high for the needs of the occupants and the air quality. Complaints were really common in that case because some sector were overcooled, of course. And in terms of energy efficiency, it means a lot of heating consumption that are not really needed. So what could be done in that case, what would be the EBCX measure, would be to calculate what would be the minimum airflow required for ASHRAE 62 to make sure that the minimum would be set at this set point. And it could be useful to validate the airflow with a balancing contractor in that case. So here's a summary of control measure. And as I was saying earlier, there's much more control measure that could be detected in the investigation process of the EBCX. But here are the most common: resolve sensor problems such as calibration, review set point, optimize equipment staging. This one is more for more complex chill water plant or heating plant, where you have a lot of different type or kind of or capacity of equipment. So a good review of the programming of the different staging of equipment is always good. Next, implement and or optimize reset strategies, such as we've seen earlier, and review optimize VAV box minimum flow set points. Next type of EBCX measures, maintenance issue, I would say. One could argue that maintenance should not be part of existing building commissioning. And it is quite true that in an ideal world, there will not be this type of problems to deal with. Unfortunately, in real life, it's very common for maintenance issue to be detected in EBCX, and they can have a very significant impact in terms of energy efficiency. So how can we detect this type of measures? First, by carrying out a good inspection of the HVAC system. It's relatively easy to detect some problems visually, such as, of course, dirty filter or coils, or even obvious mechanical problems. Next, carrying out functional tests again can also help detect maintenance problems. For example, we can test the closure of a motorized cooling valve and validate whether it is tight in a few minutes by measuring the air temperature at the coil outlets. Also carrying out a review of maintenance task and external contract, if it's the case, can help quickly detect missing maintenance activities. For example, a control system where there is never any calibration of the different type of sensors. Next slide, please. So first case scenario, during an inspection of a air handling unit, the commissioning agent notices that the heating coil is operating at the same time as the cooling coil. It could be detected by using an infrared thermometer. However, at the BAS, the heating valve is completely closed. The agent can close a manual valve or isolation valve to isolate the heating coil, and within seconds, the situation is back to normal. This shows that we have probably a leak at the heating valve. So what would be the EBCX measure? Of course, depending on the type of valve, the operator or contractor may or may not be able to repair it. And in some cases, replacement might be needed. Energy savings are often very significant in that case, since they impact several systems: heating energy, cooling energy, pumps, etc. they also have quite often an impact on comfort. Next case scenario would be a faulty economizer damper. In that case, this ventilation system must operate in recirculation mode at night. And trend curve analysis revealed that the mixed temperature at the economizer outlet is on average 4 degrees Celsius cooler than the return temperature in complete recirculation. So without further investigation, several problems are possible in that case. First, of course, a leaky motorized damper. It could also be a poorly adjusted motorized actuator or linkage, and also it could be a sensor that is offset. So in that case, I would say that there are a few resolution steps from least to most costly. First, make sure that the temperature sensor are calibrated. Next, a simple functional test of the damper would show if the damper is operating properly and completely shut off during recirculation mode. And if nothing is can solve the problem in another fashion, a complete damper replacement might be the ultimate solution. Another maintenance problem, I would say that we see that quite often, dirty cooling or heating coils. In that case, that problem was detected because the operator was reducing the chill water temperature below the design set points. And he was doing that because basically the coil were completely dirty, as we can see on the picture. And despite this, one of the air handling units failed to reach the temperature set point in summer. So, of course, this was causing comfort problem in some area, as well as reducing chiller efficiency, increasing flow rate on both the water and air side. And the problem was caused because the system was really difficult to access to do the maintenance and operation, and the filter replacement was not done on a sufficient basis. So in that case, it's a really easy measure. So check coil condition and measure pressure drop to confirm that the problem is really dirty coil. Well, in that case, it's quite easy to see in the picture. Clean coils as required, and of course include this task in future preventive maintenance program. Slide. So quick summary of the type of measure that could be classified as maintenance measures. So eliminate simultaneous heating and cooling, reduce losses in the ductwork, so leaky ductwork, filter that need to be changed, etc. Improve equipment performance, eliminate flow obstruction, and review damper and valve operation.
Thanks, Eddie. I will finally talk about the last category, heat recovery. So if you have a heat recovery system in a building, of course, you want to get the most out of it. But operation with that type of systems can be more complex than usual ones, and issues can appear. So how to spot the issues related to heat recovery? You want to review mechanical drawings and expected efficiency. You want to measure flow and temperature and maybe calculate actual efficiency. Review BAS trend logs and review control sequences. And finally, perform functional testing under several operational conditions, summer, winter, maybe mid-season. first case scenario here I want to talk about it about air-to-air heat exchanger. So you can have buildings where heat exchanger does not perform as well as expected during the design phase. Maybe operator receives many alarms during winter, and you see that you need supplemental heating even during mid-season. First question you can address is balancing optimal. Here, in that scenario, you have a dedicated fresh air system with a thermal wheel. Comparing what you observe on site at left and what you expected at right during the design based on heat recovery efficiency. You can conclude that balancing here is not optimal. Actually, airflows has been reduced, the return airflow has been reduced, and it is very different from design. So here, at left, you don't reach the set point that you expected, and maybe additional heating would be required here to meet temperature set points. Another question to address for air-to-air heat recovery: does overheating occur? So here in that example, you see it's like a good example with a good control strategy, but sometimes when heat recovery systems are not optimized, you can recover more heat than needed, and it creates overheating in rooms supplied. In that case, as I said, the control strategy was already optimized. You have, for example, antifreeze regulation. You have a sequence for enabling or disabling the thermal wheel. And you also have an optimized sequence to control bypass dampers in the fresh air and the exhaust air conduct. And with all that control strategy, you can modulate heat recovery and meet the good supply air temperature. Another heat recovery system that you can have in a chiller plant is the heat recovery chiller. So here you want to question if the HR chiller is used at the right time and under the right conditions. You can you have to prioritize the heat recovery chiller when there are heating loads in the building. And you also want to optimize heating loop temperatures to benefit the most from the heat recovery chiller. To summarize the heat recovery opportunities, here you have air-to-air heat recovery. We discussed thermal wheel, but it also could be plate type heat exchanger. So first you want to optimize the control strategy, enabling, disabling, maybe bypass damper. You want to establish or optimize antifreeze regulation, and maybe review air balancing between fresh air and exhaust. For the heat recovery, as discussed, you want to prioritize heat recovery chiller when there are heating loads in the building. You want to optimize heating loop temperatures, and also you want to overheat air when you have air-to-air heat recovery in the building. So you can use mechanical cooling and benefit from like a good COP for heating. So here it concludes our presentation. Maybe Jess, I can let the
Perfect.
Good.
Thanks, Aurélie.
Thanks.
And we had one question come in by the chat, but I think between Cynthia and Monica, we responded to that one, though Kathy, if there's any other aspects of your question, feel free to jump in. But others, now we're at the discussion point. So feel free, you can open up your mic and ask a question or raise your hand and I will call on you. Or you can drop a question into the chat for anyone from the BPA team and the content that they presented, or if you have a question about the EBCX program from Save on Energy, we can pass that to Monica or to Cynthia.
Maybe I just had one subject of discussion. I mean, it was great overall, a little bit on the surface, but obviously we don't have that much time to go into all the details that's required. I would say for the CO2 sensor value, I think we might actually consider going a little bit more into the details of, what's the actual value that you should put as a set point. Do you want to base your, like it says that it's based on ASHRAE 62.1, but it's probably a little bit too generalized, I think, as in this presentation. I think you have to put a little bit more attention of what the set points should be. That's just one consideration that I wanted to discuss. I don't know if you have any comments on that.
Well, adjusting the airflow according to CO2 level is always, I would say there's as many designers as there are ways to do it. As we said earlier, well, personally, I don't use CO2 level from the return I don't think it's a good way of doing it. CO2 level in rooms that are highly occupied or high density with a high density occupation are more, I would say, appropriate to do that. And what I usually do is I adjust the CO2 to, let's say, 500 ppm over what is the CO2 level outside. But there's a lot of way of doing it, so I won't say it's the only good answer. I don't know if you have an opinion on that, Jean-François.
Well, yeah, I would say it's probably appropriate what you're saying. For instance, there's the WELL standard that provides indication on what CO2 value should be. I think the values that were shared here, you got to be careful. It's probably the absolutely minimum requirement that is required. And also, depending on what type of space you have in the building, the concentration will be different. So I just want to make sure that people don't think that 1,100 ppm, for instance, it's like the standard. You actually have to think a little bit more about it when you choose your CO2 set points.
Absolutely, I agree with you.
Thanks, Jean-François. We had a question come in from Arda, and I think this was something that you presented on a few moments ago, Aurélie, but just asking for a little bit more detail when it comes to the anti-freeze alarms and their potential effect in the system. Aurélie, sorry, you're on. Yeah.
Yeah, you want an antifreeze regulation because if you don't have it, maybe you've got some ice on your heat exchanger and then you completely lose the efficiency of your heat recovery system. So sometimes you have a low limit to have in your exhaust line. So maybe you want to use your bypass damper just to make sure that you don't go under that low limit. And is there another question for heat recovery? Yeah.
Yeah.
There was so. Right below that, just asking for some more detail about the heat recovery chiller measure that you mentioned around overheat air and using mechanical cooling.
Maybe I can take this one, Aurélie. This measure is when you have both in the same building, let's say heat recovery wheel on exhaust, between exhaust and dedicated outdoor air system. And at the same time, you have a heat recovery chiller elsewhere in the building. And yeah, in that case, it could be a good idea to, let's say, let run the enthalpy or the heat recovery wheel at maximum speed, even if the air temperature is going over the I would say the supply air temperature set point of that system. and do some mechanical cooling to increase the load on the heat recovery chiller and send that heat elsewhere in the building. So you can increase the quantity of heat recovery you're doing in this building and make more energy saving in that case. I don't know if it answered the question, Mr. Ali.
Yes, thank you.
Could I have another question or discussion? We spoke about the trim and response strategy. I think it's great in practice. In reality, sometimes it's quite difficult to implement because of rogue zone, for instance, or it complexify the system. I do believe it's a good idea. So what's your approach to that to avoid rogue zone, or sort of, there's always this space that never gets to the right set point. So how do you manage that?
Well, one way of doing that is to simply neglect a few zones in the programming. So you could say that the first 2 or 3 VAV boxes that are over 90% won't count in the programming. And usually they are always the same. So once they are identified, you can go and look what is the exact problem of that zone. It could be a sensor that is not correctly placed in the room. It could also be VAV boxes that the actuator is completely inoperative. But yeah, usually you need to neglect a couple of zones of that because there's always a zone that is not satisfied.
Great, thank you everyone for these questions. Are there any others? I was going to just circle back to something that I think Aurélie and Megan, you spoke about briefly at the beginning, and that's, coming into, if you're just getting started with an EBCX project, and right at the beginning, thinking based on your experience and all the measures that we've just been talking about, I wonder if you could just talk a little bit about what are the 1 or 2 things that you really pay attention for in some of those initial steps that you talked about, whether that's reviewing the building energy data, conducting a walkthrough or some functional tests, or interviews with operational staff. What's that like top line 1 or 2 things that you're looking out for, listening for early on in those engagements that tip you off for a certain measure, certain opportunity?
Well,
I would say, maybe I start.
Go ahead, Aurélie,
yeah.
go ahead.
I would say first, do not focus only on the building automation system, because you will see that sometimes it doesn't reflect the reality. So just go walk the building, talk, and take some time, like a lot of time, with the operator, because they will give you tips, and it will orientate your investigation. So yeah, that will be my advice to start.
Yeah, I agree with Aurélie, because if I might add, a lot of times what is shown on the BES system is not the reality of the system that you have physically in the mechanical room. So the first thing you want to do is make sure that you understand really how the system are configured. And it can be a heating system, a cooling system, a ventilation system. Unfortunately, what is shown on the control graph is, I don't know, maybe 40% of the time not exact. So you need to understand the reality in the mechanical room.
Great, thank you. Another question just came in from Stephen, and then we'll go to Ali. Stephen's question was, why was the comment made that pumps should not be run in parallel?
Oh, in that case, it was a specific example. The pump was supposed to be completely redundant in that system. So they were designed to be completely, I would say, one pump was sufficient to do all that was required in this specific system. And unfortunately, in that case, the pressure set point was set so high that you needed 2 pumps to reach that level of pressure. And even then, so it was just a bad operation.
Great, thank you. Ali, please go ahead.
Thank you. I'm just wondering, you mentioned heat recovery chillers, and I'm curious if you have used any formulas on VES or any approaches to monitor the COP of the system, and same thing for heat pumps, based on the information available, or I'm just thinking from a new project perspective. If you would redo things to have all the information you need to maintain a high COP on your system, what would that look like? And is that something you see in the market?
Well, depending of the equipment you have, either heat pump or chillers, most of them have now a BACnet interface, and usually you can have the information on directly on the control panel of the unit. So normally you will have the COP, or you will have the electrical input and what is produced in terms of cooling energy. So you can do easily the calculation. So usually, and it's not always the case, but usually it's most of the time it's the information that is already available at the BES system. But is the COP important when you are operating recovery chillers? Not that much if the energy that you are rejecting is sent to the heating system. You don't care too much about the COP in that case. But of course, you're trying to do this as efficiently as possible. But when the heat is recovered, it's not that important, I would say.
All right, thank you.
Aurélie, would you mind just advancing the slide 1? And if anyone, are there any other questions or ideas folks want to raise?
Maybe I got just one last one.
Please.
So there's might be a lot of resistance when you get inside the building to do changes to control sequences with the operators. You're gonna obviously make the system sometimes a little bit more complicated. Sometimes you're actually fixing issues, which is great. But often, like when you do trim and response strategies, you're gonna make the system more complicated. So, how do you? And sometimes you might even, the operators might actually make you feel like you make them look bad because they're not necessarily doing their job properly on the maintenance side. So how do you deal with that?
Well, it's you're absolutely right. It's a good question. I would say it's you need to have a very good approach with the operator, and usually what we're trying to do is do that as a team and make them part of the decision, I would say, or the make them part of the idea that will be presented usually to his boss. So it doesn't make him look too bad. He's involved from the start, and you can always say that he already had the good idea, but he didn't have the mean to implement that. So it's kind of strategies that I'm using in that case.
Yeah, I think that's a very real world question based on some of the research and work we've been doing lately. Any other questions before we wrap up? Great. Well, first I want to say thank you to actually, oh, sorry. Stay on that one. I'm going to speak to what's there. Thank you. Thanks, Aurélie, Eddie, and Megan. That was great. We will be sharing the slides and recording with everybody who participated here. And then in the next week or so, all of those materials will be available on the Save on Energy training and support website. On the EBCX portion of that site in particular, the link to which I dropped in the chat. Also here you can see a link for the general training and support website. That's the, I guess, the second link down on that page. Save on Energy recently updated the list of courses for which training incentives are available. So there are a lot of in-depth training courses, things from a couple of hours to 4 and 5 day training courses with credentials at the end that Save on Energy provides 50% trainings incentive support for. So if you're interested in building your energy efficiency related expertise, by all means, go check that out and take advantage of those incentives. And then as well, here's again the link to the EBCX program site at the bottom of the page. I'll also throw out there to everyone that training and support, there's also follow-up coaching support available. So if you are a building owner or manager getting into or thinking about putting together an EBCX project and you're looking for a little support in kind of getting your house in order for that, you can contact us at Training and Support, and Save on Energy can provide that support for you. So please do get in touch and look out for our upcoming events. Our next couple of webinars, there will be a 2-part series focused on diving into the investigation phase in detail, coming up on January 11th and 18th. And then another event, I believe, coming up in March, looking specifically at the handoff and persistence phases. With that, thanks everybody for sharing your afternoon with us. Thanks again to the BPA team and Monica and everybody else.
Thank you.
Thank you, everyone.
Thanks.
Have a good day.
Thanks, everyone.